Next, we will have another of our postdoctoral candidates, Ronak Buch, who will be continuing a discussion with selected topics in load balancing, some of which include, I believe, GPUs.
Okay, so thanks, Eric. Like Eric said, my name is Ronak Buch. I'm a PhD candidate in PPL. And this is sort of the Jeopardy potpourri category of dynamic load balance. We're going to cover a bunch of different stuff that happened that weren't large enough to make their own talks, but were still significant, and I'd like to talk about them today. As you can see, this is sort of a large collaboration. So lots of other students helped with a lot of this load balancing work. So it's myself, there's Kavita, Juan, Haojin, Harshita Menon, and Michael, who just spoke. So to give you a brief overview of what the talk is going to go like, I have an introduction, then I have a few topics I want to talk about, including greedy refine, topology-aware load balancing, heterogeneous load balancing, a load balancing library we've produced from Charm++, and then finally a conclusion. So just for a bit of background, as you probably all well know, load balancing is a very, very key facet of Charm++. Without the dynamic load balancing framework that we have, we wouldn't really be able to achieve the scalability and performance that Charm++ offers as a hallmark compared to a lot of other parallel programming frameworks. And this has been around for a long time. We've had lots of different strategies, lots of different variety. We're always trying to make it better. So the main things we focused on this time were new algorithms to improve performance and new approaches to tackle different sorts of hardware that we're seeing in modern machines. So I guess I went over this briefly already, but we've added some new features to load balancing infrastructure of Charm++. So we have improvements to the standard greedy algorithm, which is one of the base load balancers that is very commonly used in Charm. We've had topology-aware load balancing that sort of plays on the topology-aware mapping work that we've had in the past, but now introduces a few new variables and makes some improvements to that. As Michael touched on, we've had some progress in heterogeneous load balancing, and we have two different ways of doing that, so I'll explore them and explain them a bit when I get there. And then finally, this load balancing library that splits off the load balancing infrastructure from Charm and makes it available to use in MPI or other sorts of applications. So the first thing I'll talk about is greedy refine. So as just some background, I'll go through the way the greedy algorithm works in Charm++. A lot of you probably know this already, so I'll go quickly. But essentially the way it works is it takes all the objects in the application, puts those in a max heap, which you see over here. So in this case, we have three objects, object A, object B, object C, and they have different loads. We have two PEs, PE0, PE1. Right now, they both have loads of 0. So we just go through every iteration. We pop off the top object, put it in the PE that has the lowest load currently. So here we see we popped off 90, put it in PE0. And now we have our lowest PE is PE1. So then we pop off 50, put it in PE1, and then 40 goes right there as well. So in general, greedy does a really good job at balancing load. I think theoretically, it's within 4/3 of the optimal load distribution that we can find. One of the issues, though, is it doesn't consider locality. All we care about in this is the maximum load and the minimum load on the PEs. So one thing you'll see often in greedy algorithms, for load balancing in particular, is that often almost all the objects are moved around. And we can usually do a pretty good job, get close enough to what the greedy would give us without doing so much migration. So if you don't want this really high communication cost, what do we do? So we can do better. And like I said, we can modify greedy LB to limit the number of migrations that happen. So in order to do this, we introduce a new load balancer. It's called Greedy Refine LB. It's out in Charm mainline. It's going to be in 6.8 if you get the new release. And it's basically the same as Greedy LB. But in every step, we decide whether to assign the object to the least loaded PE or to keep it on the same PE that it started on. So I'll explain the criteria we use. So we pick two values, alpha and beta, greater than or equal to 1. We look at the least loaded processor. We look at the previous PE, which is when you enter the load balancing phase where the current object is located. And then we look at the maximum load of a greedy LB solution. So we do one iteration of greedy and see what that would give us. And we multiply that by some alpha, again, some threshold greater than 1. Then, if the load of the PE that contained the object before load balancing is less than or equal to beta times the load of the least in the entire system, and if we keep the object on the current PE, and if that's within some percentage of the maximum load that greedy gives us, then we just keep the object there. Don't do anything with it. Otherwise, we put it on to the minimum processor. So what this ensures is that we're always within some constant factor, alpha in this case, of the maximum load of what the greedy load balance solution would give us. So let's go through some results. I'm going to go through a few different results here, and we're going to vary alpha and beta and see how that affects the whole thing. So let me explain this graph briefly. So on the left side here, it is, on the x-axis, we have different kinds of load balancers. On the y-axis, we have the max load. This is normalized to what greedy provides us. The right side, we have, again, the same load balancers on the x-axis. On the y-axis, the percentage of objects moved. So as you can see, one very clear thing here is that greedy in percentage of objects moved is basically 100 all the time. I'll mention one more thing. All these results are the combination of 12 random-ish distributions of data. So none is the no load balance case. So here we move no data at all, and we see that the load varies wildly on all the 12 samples that we have. Refine and refine swap are sort of beyond the scope of this, but they try to minimize the objects moved at the cost of not offering that great a load balance. Greedy refine is the second one in both of these cases. So you can see here, greedy refine offers load very, very close to greedy, but the median migration is below 20%, right, as opposed to greedy, which is above, or basically at 100 all the time. But we can tune this if you want different preferences on how your load balancing works. So here, we allow a little bit more load deviation in greedy refine. And you see our median objects moved goes down even further. There's one outlier up here, but we've compressed the range of which we're moving objects. We can continue doing this. So now we have, you can see a little color now, but still very, very close to what greedy provides you. And now the median moves is basically on par with refined swap, which tries intentionally to minimize migrations. So in this case, we try to achieve a good balance between migrations and total load. So an obvious question here is, how do we pick alpha and beta? It's kind of hard to do this in general for applications. Even for different systems, networks can change a lot, and the amount of load balancing you can tolerate changes a lot as well. So what we do is we want to try multiple values and get the best result. Basically, use an ensemble method, find the winner, use that. The trouble is we didn't have a way in Charm to do this before. So we thought about this, and we just implemented a new mode. So we have this new mode called Concurrent Mode that is implemented in Central LB. So if any of you have your own custom load balancers, you can easily use this. All you have to do is set the concurrent flag to true, and you call apply decision on the PE of the best solution. It'll use that as its load balancing strategy. So for example, greedy refine LB, we have 225 different parameters. So alpha times beta equals 225 in this case. Go through the entire thing, and we choose the best one. And we do all this in parallel. And the way we choose the best ones, we use the fewest migrations with a max load under some threshold of what the greedy would provide you. So we've had a lot of tests where this performs really, really well, as you saw in those results. This is mostly done by Juan with some help from some other students. But this seems like it's a much better default to use than what we've used in the past, which is greedy. And this gives you a lot of leeway in tuning exactly how much migration versus load you want. So moving on to topology-aware load balancing. One thing you may be familiar about, we've had lots of papers, lots of history with topology-aware mapping. There have been a lot of papers from our group and other groups as well, showing that this improves the performance of MPI and Charm++ programs a lot. We saw Tom was mentioning it in his talk about Changa, about how blue water scaling results are much better than other ones because of their topology-aware mapping and things like that. So the reason this happens is reducing the distance that messages have to travel. Both just innately, you travel less distance, you go through fewer links, fewer routers. So it's faster to do that. But you also reduce the likelihood of contention. The less time you're out traveling, the less likelihood you're going to bump into someone else. So rather than just placing ranks or PEs based on this information, what we can do is dynamically map objects based on topology, load, and communication. So use all the variables we have at our disposal with this dynamic runtime system. It's a bit more sophisticated than just static mapping, as you would often get in MPI. But this really helps. Now we can cope with changing communication patterns, changing load, and things like that. So again, we saw this problem and implemented a new load balancer to take care of it. This is called gTopo-COM-LB. The G stands for greedy in this case. It's a load balancer that combines load information with communication topology, as that's not evident yet. Again, one of the things we have to do here is perform multi-objective optimization. So we try to minimize hop bytes. Hop bytes is just the number of bytes sent times the number of hops you go on the network. We have to do this while satisfying some maximum load tolerance. So again, we're basically taking some acceptable load, and we're saying we have to get below this, minimize the hop bytes. Again, this is sort of a hard thing to do, because if it's too low, you can be infeasible completely if there's no polygon under the line. Or you make it so low that you have to get a high hop byte count. If it's too high, then hop bytes might be really low, but your load all might be on 1 PE, for example. So again, this concurrent mode that we implemented shows up here as well. We use concurrent mode to run multiple instances with different maximum load tolerances, and then pick whatever we think is the best one. So some results for that. This is on Blue Water's 1K nodes, 16K processors, 64K objects for a regular stencil in 3 dimensions. One load balancing step iteration 15. This is a pretty static load balance problem because it's stencil. So we see that the maximum load is 2% higher than what GreedyLB would provide us. But the hop bytes is 7 times smaller than what GreedyLB can provide us. Especially on a machine like Blue Water's, this makes a really big difference. We get 49% higher performance than DummyLB, which does no motion of objects. And we don't even have GreedyLB results in here because it just increases contention on the way that it arranges things when you actually do this load balance. So this has proven to be really effective on machines and for applications that are really communication dependent. So now switching gears a little bit, I'm going to sort of build on things that Michael talked about in the last talk and cover the progress we've made in heterogeneous load balancing. So again, I'll probably cover a lot of things that he said before, but GPUs and other accelerator devices have kind of changed what we need to do to balance load in HPC systems. There's lots of different challenges here. One of the biggest things, it's very obvious, different hardware can have different performance for the same work. Right? Doing a matrix multiply on the CPU versus the GPU, you'll get radically different performance figures. One very important thing is that data movement overhead can outweigh hardware performance gains. So if you've used GPUs before, you've seen the latency to copy data across the PCI Express bus can kill your performance, even if you have a really, really fast kernel. And then the execution model varies a lot on the hardware target. So GPUs might have to agglomerate. You might have to make sure that your code is SIMD-ish and stuff like that. So you have to consider different aspects of your actual implementations and how you execute them and how you batch them. Another big thing is that some programs may only have CPU work and GPU work that you can't translate from one to the other. So this is how, if you write an MPI program with an explicit CUDA kernel, there's no automatic translation between CUDA and x86. But there are some ways, for example, the Excel framework that Michael touched on, where you can write code that can be executed on any device if you have multiple implementations of the same functions. And there are others still that could have both. You could have some things that could translate, some things that can't translate. It becomes a very, very complicated hodgepodge of tasks. So we have 2 different solutions for this. The first one I'll touch on is this thing called vector load balancing. So I remember this from Eric's talk a few talks ago. In this case, what we care about is CPU work and GPU work. That's all we care about right now. We have some future plans to extend this, but this is our main focus. So essentially what we do is we use the Charm++ runtime when people use GPU Manager to measure the load on the CPU and on the GPU. So now every object, rather than having a single value, as it used to in the load balancing framework, and now it's 2 values. So it has a CPU load and a GPU load. Our main problem here is that we want to distribute this work such that both dimensions are minimized, and the variance across the entire system is low. So what we're doing right now is using greedy strategies to place these objects. We basically either take the same heaps that we illustrated earlier and take the maximum of the vector and use that to balance, or we use multiple heaps, and we pick based on what the current maximum dimension is and use that to select the processor or object. Well, currently, this is a work in progress. We're looking at using other algorithms as well. Maybe there are better solutions for this, and that's a topic of research right here, right now. So to give you some quick results, this is obviously a very synthetic benchmark. These are object loads. So we have 8 objects in this case, all with the same CPU load of 1 and an arithmetic progression of GPU loads. So it's a very, very simple case. But if you just run a regular greedy load balancer on it, you see that the CPU loads are perfectly balanced, of course, as they should be here. But the GPU loads have a pretty high variance because it's not considered at all. This is a very, very clear example. If instead we use a vector load balancer, lo and behold, all of the GPU work is the same, all the CPU work is the same. And of course, this is a very contrived synthetic test, but it proves that our system at least works. But we went on and used it on actual, more production applications as well. So here's one we have in Changa. This is with just regular dwarf test set. We have no LB, so no load balancing at all, a distributed load balancer, refined LB, and a refined vector. And here we couldn't really observe that much. And this is obviously a GPU version of Changa, if that's not clear. We didn't really observe much gain in using this vector load balancer. Our suspicion is that the examples we're using have a lot of CPU load, and basically the GPU load we're balancing doesn't really matter in these cases. But we're looking for more cases where GPU load matters more. We can get some useful data out of this stuff. So hunting for a problem right now. We have the solution, trying to figure out where to apply it. Switching gears slightly, so this is moving on to the case where we have load, or you have work that can be translated from CPU to GPU or vice versa, if we have multiple implementations of tasks. So this, again, fits into the Excel framework that Michael explained in his talk just recently. This is obviously a different problem since before this, there was a static division of labor. We had some CPU work, some GPU work, and that's it. Now we can translate stuff around. We don't really know the functions. How do we take one unit of CPU work, convert it to GPU work? So what we have to do is find the optimal split point to divide the work evenly. Obviously, different workloads react in different ways, and we don't know these things a priori. They can change based on the load of the GPU. They can change on the system, change on the application. So what we do is dynamically assign work based on some strategy. So I'm going to show the same results that Michael just showed. Probably tell you the similar thing. But just to beat them into your head, we have different systems. You can either specify static assignment. So the user can say, put 50% of my work on the GPU, 50% on the CPU, and let's just use that. We also have dynamic systems where we do hill climbing or other sorts of algorithms where the runtime will try to find the optimal point. So again, if we go through these things, we see that sometimes there are discontinuities that can make this slightly complicated. We can obviously solve these things, but it's not super trivial. And again, in this case, we try to find somewhere in this region where the load is minimized across both. And then for MD, we have a different split point. We try to find something more on the right half of the graph with more work going to the GPU. So again, this is a work in progress. We have things working with example applications. Now we're basically trying to extend that for more production applications to try to see benefit. So briefly, the future work, like I said, we're trying to combine the vector load balancer and Excel load balancing together. So this can provide a more holistic response to shifting load. We can move objects from PE to PE, and then within that, try to find the set point based on the new work, based on how much GPU load there is there, and just be more responsive to shifts in load. One of the things I mentioned as a problem was that data movement is a big thing with accelerators. Right now, we don't consider that at all. We have some annotations to instruct the runtime to leave data on the GPU, but we don't use that to determine scheduling strategies. So that's one thing that's very important. One thing we're planning on adding is cognizance of where the data is, and be able to say, even if your GPU kernel is much faster, if the GPU kernel time plus the transfer time outweighs the CPU time, then we just execute there. So cognizance of this, I think, is very, very important. Finally, something that Eric was talking about in his talk was adding additional constraints to the vector load balancer. So we could put things like a maximum memory threshold to make sure that applications with a big memory footprint don't start swapping, or we try to make things so they all fit in cache. You can really improve performance of certain programs. Or for things like PDES, even provide application-specific parameters. So if you have some metric that you track in your application, just feed that in the load balancer and use that. Why not? Finally, the load balancing library. So just a brief summary. So what we've done is we've decoupled all the load balancing strategies that we have in Charm. Well, not all of them, most of them, and released them as a library. They're available at this link. These slides will be online, so you can access them there. It's mostly designed to be used with MPI. You could use it with other applications, but that's obviously the case we're going for, since most people use that for HPC. We have a feature to automatically measure computation and communication. Basically, you can register your work, and it'll automatically be measured by some library calls, or you can pass them in manually. One thing we don't have is a mechanism for migration. Obviously, in Charm, we have pup. Pup is technically decoupled from Charm, so you could use that in MPI if you wanted to. But we've sort of punted on that and left that up to the user, because they should have more cognizance of their application. But if you can provide this data to the library, you should be able to use all the strategies to determine where to place different objects without using Charm++. OK, so to wrap up, we've implemented a couple new load balancers. We have Greedy Refine that provides more parameters to Greedy and lets us control migrations. We have gTopo.COM-LB, where we use topology over mapping to try to reduce communication on machines where that matters. We're currently working on a bunch of different strategies for heterogeneous load balancing, some of which are useful now, some of which aren't yet, but we're looking for more places to apply them. And then finally, we have this load balancing library where we've exported the expertise we have in load balancing for more people to use. All right, that's all I have. Any questions?
So just a quick question. So you've taken the load balancers from Charm and put them in a separate library. Is there a mechanism that further progress on the Charm side or the MPI side will cross-pollinate, or is this just a fork that?
Right now, it's just a fork. Ideally, there weren't really that many changes from the Charm side to the external side. We basically determined our own API since no one else has one officially. So we were thinking about just making it the same, and when you build Charm, you just link in that library rather than using the ones built into Charm. So it would be the same code base. But we haven't done that yet.
Quick question. Apply decision needs to be called by the user?
It has to be called by the load balancer.
So who is making the choice and how? That's
So the way-
completely hidden from you.
Unless you write a load balancer, yes. Yes.
So if I write a new load balancer, is there any way I can test that except for just running it in my application?
Well, so right now, I didn't mention in this talk, but we have some other work going on. We're building sort of load balancing testing scaffolding. So right now it's written in Python, but we intend to let it interface with Charm++. There's an option in Charm where you can basically write your loads to disk and then load those later on. So essentially it's going to be like a scratch pad where you can easily mess with algorithms in Python, get lots of statistics on how long things take, what the loads are, what the mappings are, and then maybe even a way to put that directly into Charm as well. So yeah, there are some other topics we're doing in load balancing that I didn't touch upon, but that's an area of research right now.
All right, let's thank our speaker.